So, hope everyone had a good spring break. And yeah. Okay, so I guess it's time to start. So I see the homework this week is a little tougher than usual. So, and that's because we're starting to do some more interesting things with the Poisson process. And yeah, so I thought we'd go through the homework, but before that, I just wanted to go through some of the theorems that are used in the homework, which are very important. And you've probably seen them before, but I think it would be useful just to, if anything, just write them down so that you remember them. So, first of all, let's start off with proposition 5.2. And this is what's called the Poisson thinning property, which is used extensively. It's very important. Okay. And so basically the setup is the following. You have a Poisson process. So this is a Poisson process with some rate. Say the rate is lambda. And you have events that occur according to this process. But now, each time an event occurs, it is classified as being of a certain type. So it is classified as being type 1 with some probability, let's say probability p, and type 2 with probability 1 minus p. And p is a constant probability. And we will see that we will generalize this to where we allow the p to depend on the time at which the event occurs. But that will come later. So we have this Poisson process, and events are classified in type 1 and type 2. Now, if we denote by n1 of t the number of type 1 arrivals up to time t, and similarly n2 of t, the number of type 2 arrivals up to time t, then this proposition tells us that n1t and n2t are independent Poisson processes with rates lambda p and lambda 1 minus p, respectively. So if we were to look at this as kind of a schematic diagram, we have arrivals into the system at a rate lambda, according to a Poisson process, and then we classify events as n1 as type 1 or type 2. So this is n of t, and then we have something like n1 of t, which is again a Poisson process with rate lambda p, and n2t, which is a Poisson process with rate lambda times 1 minus p. So this is kind of what's called the, you see why it's called the thinning property, because process is literally sort of broken in two. And what this theorem says, and it's very important, is that both n1 of t and n2 of t are independent, and they're Poisson processes, and they depend on this probability in this way. So that's an important thing. Now, another very important fact, which we touched on briefly the other time, is Theorem 5.2, which basically says that say that n events occur by time t, and we're interested in finding the distribution of these n arrival times. Well, what this theorem asserts is that the distribution of the arrival times will be the same, conditional on n events having occurred, will be the same as the distribution of the order statistics of n independent uniform random variables, uniform on 0t. So in other words, this means that the joint distribution of the arrival times, of the n arrival times, up to time t, this will be distributed as the joint distribution of the order statistics, U1, the order statistics of n independent, the UIs are independent, uniform on 0t random variables. So in other words, it doesn't matter about the order statistics thing, but what this literally means is that if, you know that n events have occurred at time t, so in this case, n is 5, then you would expect that these events are distributed uniformly on this interval. So, in other words, the probability that, they're all, so, an example would be the, well, actually, so, in other words, the density of this, of a specific sort of configuration of these arrival times would just be equal to n factorial times, what was it, t over n, over t to the nth power. Just want to make sure I don't make a mistake here. Yeah, so it would be n factorial over t to the n. So that's something that is also very, very useful to remember. And sort of there is a proof about this, but why this is the case is that if we know that these are equal, so this is just equal to it's in the book. I think I shouldn't really butcher it here, but you can check out the note on the order statistics in the book. But no, I think I might as well write it down, because this looks a little mysterious, but shouldn't be, because so the probability of of this event occurring is equal to n factorial times the individual probabilities times the product of the individual probabilities. Well, why is that? Because, so say that we have, sort of this event occurring. So the first order statistic is like a little u1, second is a little u2, the nth is a little un. Well, we will get, first of all, for the order statistics to be this way, well, this realization of the random variable has to occur, right? So we have to have one random variable be equal to little u1, the other be equal to little u2, so on and so forth. But now, any one of those different configurations can result in the order statistics being this way. So we need to add up over all the different permutations the probability of this realization of the random variables. So in our case, we know that for a uniform random variable, the density is just 1 over t everywhere. So that's how we get that it's n factorial over t to the n. So I know I didn't do a very great job of describing it, but that's sort of the logic, and you can refer to the book for much clearer sort of argument. But yeah, so that's theorem 5.2. So, and the only reason I sort of mention it is because theorem 5.3, or is it a theorem or a proposition? I think it's a proposition 5.3. The proof of it is very heavily based on this fact. So what does proposition 5.3 says? Well, so we have the same setup as proposition 5.2, only now events are classified in k different types. And we also know that if an event occurs at time s, or at time, be consistent, at time s, then it will be type I with probability PIS. So in other words, we allow this probability to depend on the time at which the event occurs. Note that this is a generalization of the previous theorem, because here, we can say that this depends on time, but we can say that it's just identically equal to P for all time, for all different times. So this is a generalization of the previous theorem. So now, given this setup, we can again say that NIT, the different processes NIT, so the number of type I events until time t, these are independent Poisson processes with means equal to lambda times the integral from 0 to t of PIS ds. And you can look in the book for sort of a derivation of that, but the just kind of the intuition is that so intuition, you don't really need to write this down or anything, is that if we say that P, say that a random event occurs at some time, right? So, so given an event occurs at time s, it is type I with probability PIS. Now, we know that when n events have occurred, the distribution of their arrival times is uniform, right? So if we were to say, if we were to consider the little probability P of being the probability of an event being type I, well, we would have to condition on the time at which it occurs, right? So this would be probability type I given that it occurs at time s times the probability that event occurs at time s. So, and we take this from 0 to t. Now, we know that this is just equal to PIS. And we also know that conditional on n events occurring, the arrival times are distributed uniformly on 0t. So this would just be 1 over t ds. Wonder if it's visible. Okay. Can everyone see this? Sorry. I'll continue here. So we sort of have that our P here, probability of a random event being a type I event, is just equal to 1 over t times the integral from 0 to t PIS ds. And then remember the proposition 5.2. So then we will have the, NIT will be Poisson process with rate lambda t times p. No, will be a Poisson random variable. Poisson with rate lambda t times p, because this is what proposition 5.2 says. And so in this case, we have lambda times t times 1 over t times the integral PIS ds. So that's kind of how we get this. Sort of a rough sketch of the proof, but just so that you don't think that this sort of comes out of nowhere. Okay. So is everyone kind of clear about this? Because as you probably saw in the homework, this stuff is used over and over and over again, especially that theorem. That's the little more complicated one. But just to illustrate now the usefulness of these theorems, I'll do an example that's in the book, which sort of pops up everywhere. So here's example 516. And this is the mg infinity q. So here we have a queuing system with an infinite amount of servers, where events occur according to a Poisson process with some rate, and each server serves with a common distribution of g. It doesn't have to be exponential. It's just a distribution g. So arrivals according to a Poisson process, say rate lambda. Service times are distributed according to some distribution g. And we have an infinite amount of servers. And now we're interested in sort of if we define as x of t to be the number of people served by time t, and y of t to be the number of people not served by time t, we want to figure out what the distributions of x of t and y of t are. And yeah, so we want to figure out the distributions. We want to see if they're independent or not. We want to do a whole bunch of these things. So this is a classic example where the previous theorem is very useful. Because, so, this is kind of a complicated problem because we allow, it's not the amount of time that a person spends being served is random. It's not deterministic. So let's see what we can do. So the solution here is to very conveniently call a customer an arriving customer type 1 if his service is if he has completed service by time t, and to call him type 2 if he hasn't. So let's call a customer an arriving customer type 1 if has completed service by time t, and type 2 otherwise. Okay? Now, and we know, so we classify them in this way, and they're classified independently, right? There's no dependence between them. Like if one guy is type 1, because there is an infinite amount of servers, it doesn't affect sort of what's going on with the other guy. So they're classified independently as being type 1 and type 2. And now let's see what PIS is. PIS is the probability that, let's say P1S, we only have 2 types. So P1S is the probability that given that someone has arrived at time S, he will be type 1. Okay? So what does that mean? It means that given that he's arrived at time S, he will have to have completed service by time t. So complete service time t, given that we have arrived at time s. So, okay, so what does that mean? Well, and how can we have with what probability do we complete service by time t if we arrive at time s? That means that our service time has to be less than or equal to t minus s, right? So this is g of t minus s, because, if this is time t, we arrive at time s, here's the arrival, and we need to have left the system by time t. So our service time has to be less than or equal to t minus s. So this is P1s, and similarly, P2s is just g bar, which means 1 minus g of t minus s. Okay. So now here's where this theorem comes in very handy, because we know, given this setup, that n1 of t now, so x of t, so by theorem 5 or proposition 5.3, we can immediately say that x of t will be Poisson process with rate, actually, let's say, which is equal to lambda times 1 over t times the integral g of t minus s ds, which is equal to lambda times 1 over t times the integral from 0 to t of gs ds. Because, here we're adding something non-negative. I mean, I think you can see how these two integrals are the same, right? It doesn't sort of matter where we start integrating from, which is basically what's going on here. So this will mean that the expected value of x of t will just be equal to lambda, as the theorem again says, 0t gs ds. And similarly, y of t will be a Poisson random variable with mean. I mean, it's going to be a Poisson process. So yeah, let's be consistent. So it will be a Poisson process with rate lambda times 1 over t and therefore expected value of y of t will just be equal to lambda times 0t gs ds. So let me actually check something. Yeah. Yeah, so I think this is okay. So are there any questions on this and how we apply proposition 5.3? Let me just... No questions? Okay. 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 So where should I start erasing from here? See, but I think I might be making a little mistake here because I'm saying, I think what the theorem says is that ni of t will be Poisson random variables with these means. Because it seems kind of weird to me to say that you have a Poisson process with a rate that depends on time t, on what time it is, on what the time horizon is. So let's say these are Poisson random variables. I think that's, and let's actually correct this. I mean, I'm not sure if what I wrote is, I mean, it's just kind of a subtle point, but I don't want to create confusion. So let's say that so xt, will this be a Poisson random variable with mean but I mean, I think what I wrote is correct, but it's not exactly the statement of the theorem. And of course, x of t and y of t are independent. Yeah. So if I made a mistake, I'll send you an email. But that's sort of that's the big thing to remember here. That theorem or proposition 5.3. So now, okay, let's go on to the homework. So are there any problems you'd especially like me to do? Just because there's a lot here, and I don't know if I'll be able to do everything. No requests?
81.
What's that? 81? Okay, yeah. Yeah. Okay. So I'll definitely do 81. I'll start off with 63 though. So okay. So we have an infinite server queuing system where the service times are exponential. So we have the infinity queue. And we denote xt to be the number of customers at time t. And we want to find the following two quantities. Okay. So this is a pretty good problem. So we basically want to find out, given that at a certain point in time, time s, we have n customers being served, how many customers will be in the system at time t plus s, given that at time s we have n. So, well, we first of all one thing to note is that we need to differentiate between two different types of customers, right? Because right now we have customers that are already being served, and then we have customers that are going to arrive between time s and t plus s. So we sort of have to distinguish between them. So let's say, as Professor Witt has written, so let y be the number of customers in the system at time t plus s that were present at time s. And let z be those number of people, of customers in the system, blah, 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 at time t plus s that were not present at time s. Okay. So then, we can write xt plus s as the sum of y and z. And so now let's figure out kind of, so we can also write then okay. So now we need to figure out the distributions of these two guys. So let's see. Okay. So what is this distribution? Well, we know that at time s we have exactly n people in the system. And we want to see, given that we have n people, how many of those people will still be in the system at time t plus s. Okay. So I say that this is a binomial random variable with parameters n, and the p in this case is just e to the minus mu t. So why is that? Because you can sort of imagine that we have, we have these n people here. So 1, 2, n. Now, each one of those will independently have, continue to be in the system with the probability that its service time is greater than time t, right? So what is that probability? It's e to the minus mu t. And we know by the memoryless property, it doesn't matter when these people arrived. It just matters that they're there at time s, and their future service time will be independent of anything that happened in the past. So now, given that they're there, they will be independently still in the system with probability e to the minus mu t. So that's why this just becomes a binomial random variable. It's like trials. You have n trials, and how many will result in a success? When the probability of a success is e to the minus mu t. Does this make sense? Okay. Okay, so we figured out this. Now let's see what this distribution is. Now, okay. So, does it matter? Does this conditioning matter here? I mean, I say it doesn't because, you know, here we're talking about new people who arrive into the system, who will be, and we have an infinite amount of servers. So, what does it matter if already, you know, n servers are busy at time s? So this will just be, this is equal in distribution to just z, because z and x of s are independent. Since okay, and now, so we need to figure out just the distribution of z. So now again we do the familiar thing where we call someone type 1 and type 2. So we call a customer type 1 if at time t plus s still in the system. Okay. So then, what is P1 of y? Well, it would just be e, yeah, because we're assuming that g is exponential. So it'd be e to the minus mu t minus y. Right? Because this is just equal to t plus s minus y, I'm sorry. Oh, no, it's t minus y because we're assuming that they're there at time s and it's memoryless. So then by proposition free, z will be a Poisson with mean lambda times 0t of e to the minus dy, which is equal to lambda here t e to the minus mu y dy, which is equal to if lambda times 1 minus e to the minus mu I. Or mu t. Oh, divided by, yeah, divided by mu. So any questions on this? Well, because, you know, this is exponential, right? So, yeah, we integrate here, and, you know, a mu is missing here, so we add it and also divide by it. And then this is just the CDF evaluated at point t. Yeah.
It says 1 minus e to the, I can't read it.
Oh, e to the minus mu t. E to the minus mu t. And actually, just going back to what I said earlier, I would like you to remember this theorem in this form, because I think that what I told you that there are independent Poisson processes with those rates might not be right. So just remember this theorem in this form, and I'll look into it and let you know. I don't want to be coming up with my own theories. So, okay. So we're almost done because so then this is the expectation of a binomial, right? With parameter n and p is equal to e to the minus mu t. And this will just be equal to lambda times, or what did we write here? Lambda times 1 to the 1 minus e to the minus mu t over mu. So we just add these up and we get the expectation. Okay. Now, the variance, given xs is equal to n, will just be equal to the sum of the two variances, right? Because y and z are independent. So this will just be equal to the variance of y given xs equal n plus the variance of z given xs is equal to n. So what is the variance of a binomial? Well, it's just n times p times 1 minus p. So this is n times e to the minus mu t times 1 minus e to the minus mu t. And then the variance of a Poisson is equal to the mean of a Poisson. So the other is just lambda times 1 minus e to the minus mu t divided by mu. And this is true because y and z are independent. So, any questions? Yeah.
We said p1 of y equals e to the negative u times t minus y. I'm confused by the parentheses. That's supposed to be equal to g bar of t minus y, right? It's equal, right?
Yeah.
You got parentheses. You look
Yeah,
at
yeah. It was just kind of, it's comparing it to the previous thing. And note that kind of a subtle thing to say about this is that it really matters here that we have exponential distributions, right? Because we know that these guys are in the system at time s, and we want to see if they're in the system at time t plus s. So it doesn't matter, in other words, how long they've been in the system beforehand. All that matters is that they're in the system at time s, and the time window is of length t. So this is where really matters that we don't just have a general sort of distribution, but it's memoryless. But it's the exponential. Yes?
When you evaluate the mean for the Poisson expression, the first expression, e to the power of minus mu t minus y dy. I mean the next line.
Yeah.
Yes. For the first expression, the second expression, how do we get from minus mu t into t minus y, and the next expression is minus mu y? How did that happen?
So the question is how we go from here to here.
Yes, yes.
Well, this is just look at these two integrals,
Yes.
right? Aren't they the same if you think about it? Because here we start integrating from 0. And, it's e to the minus mu t, okay? So it's just kind of a change of variable thing, because these two will give you the same result, right? Whatever value you get in here, you'll get in here. It's just kind of symmetric. See, because these two integrals would be the same if you started integrating from t here and 0 up to 0 and had a minus sign, right? Just see the look at the limits and look at what's going on. Do you see that? It's the same, and it's just the same integral. I mean, of course, we could do, we could say that, say that z is equal to t minus y, and we can do a change of variable and change the limits, and we'll get this. Okay. Any other questions? Okay, so let's move on then. So let's go to problem 81 now, which is, yeah, it's a little complicated. So, and then we can go back and do some other problems. But 81 is a tough problem. Okay. So let n of t be a non-homogeneous. So this is a non-homogeneous Poisson process with mean function m of t. Did you do non-homogeneous Poisson processes in class? No? You didn't? Yes, no, maybe? I'll take that as a no. So let's first define what a non-homogeneous Poisson process is. So definition first. And just so that I don't make a stupid mistake, with intensity of t, if, okay, so at 0 we have 0, 2 we have independent increments, those other two properties are kind of, yeah. I'd say the important thing to remember is that if m of t is equal to this integral, then n of t plus s minus n of t is Poisson with mean so in other words, is equal to so we see that time intervals are not homogeneous. So in other words, the distribution of this random variable does not only depend on the time window between the two different times, right? It actually does depend on when you start and when you end. So that's kind of the big difference between non-homogeneous Poisson process and a regular Poisson process. And there are two more properties that I guess we should write here. So. Little O of H and I think, all of these properties 1, 2, 4, and 5 prove, you can prove that then this follows this kind of distribution. But this is the major thing to remember. The rest is kind of theoretical stuff. Okay. So now let's do the problem. Okay. Okay, so we have this non-homogeneous Poisson process, and we want to show that the unordered set of arrival times is so. So this follows, has the same distribution as n independent variables distributed as fx is equal to mx over mt So the unordered arrival times. I guess we can show that the ordered ones have this distribution times n factorial, and that sort of shows that the unordered ones are distributed like this. Okay, so let's start try and do this. So. So we want to kind of find the density of these arrival times. So what we have to do is to find these probabilities for all I equal 1 to n, or this probability, and then sort of take all the hi's to 0, and that's how we get the density. Okay. This is the probability of exactly one event in ti plus hi, and no events elsewhere for all I, for I 1 to n, no events elsewhere. Okay. Yeah. Yeah, sure. Sorry.
There's a probability of ti less than si less than ti plus hi, count and I can't read as I equals.
For I equals 1 to n. Okay. And this is, of course, divided by probability that nt is equal to n. Okay, so now before we go further, let's just write what this probability is. So this, we know that because it's a non-homogeneous Poisson process, we can just directly say that this is e to the minus mu t times, or mt to the n divided by n factorial. Okay? So the denominator is easy. Now the numerator is is a more hairy thing to calculate. Okay. So the numerator. Okay. So we can start sort of taking it one at a time, right? So right? So this has to happen. Then we also need one event in T2 plus H2. Let's actually say 0 events. And T1 plus actually and so on and so forth, right? Up to one event in tn plus hn, and 0 events in tn plus hn, and t. So this is kind of what the numerator is saying. So let's try and calculate it. Now we know that we have independent increments. We do not have homogeneous increments, but we do have independent increments. So let's see. So we want one event in this interval. So what is the probability of this? Well, it's e to the minus m of t1 plus h1 minus m of t1 times m of t1 plus h1 minus m of t1, and it's raised to the first power divided by 1 factorial. We don't need to worry about that. Okay? Now, what is the probability that we get 0 events in this time window? Well, this is just e to the minus m of t1. Okay? So now let's do the same thing for the second event. So this is times then e to the minus m of t2 plus h2 minus m of t2. And now we want 0 events in this time window, times e to the minus m of t1 plus, m of t2 minus m of t1 plus h1, and so on and so forth. So times e to the minus m. Sorry, this is, I know this is a little, a lot of notation and stuff, but there's really no other way to do it. M of tn times e to the minus m of t minus m of tn plus hn. Okay, now does everyone see why this is the case? Sort of just breaking down every time interval and expressing this probability. So yeah, just a second. Okay.
The terms of the T1, like Ti plus Hi minus M.
Sorry, can you say?
Because these are, you're doing all the different events, right?
Yes.
So why do you only use the M times, or M of T1 plus H1, that term, the first time?
Well, so we're breaking down this probability. Now, we want one event to occur here, right? So this is the probability of one event occurring in this time window, of exactly one event occurring. But we don't want just that, though. We want no events to happen here. So we have to also, we have independent increments, which is great, which means that we can just multiply times the probability that no events happen in this time window. And this probability is just e to the minus mt1. And now we do then the same thing for the second event. Now, but now here, the time window is different. It's t2 plus h2 and t2. And so we want exactly one event. Oh, shoot, did I forget to? Yeah, I forgot to multiply something. Okay, was that your question? Thank you. Okay. Yeah, so thank you very much for reminding me. Yeah, well, I'm stupid. Okay, so m of T2 plus H2 minus m of T2. And then same thing here. Times m of Hn minus m of Tn times e to the minus m of t minus m of Tn plus Hn. Whew. Okay, thanks a lot. Okay, does that make more sense now? Okay. So as we'll see, we get a whole lot of cancellations here. And what we end up with is, I mean, you can see that all of these terms, basically everything except for e to the minus mu t is going to disappear, right? Because we have e to the minus mt1 plus h1 here, then we have e to the, where do we have there? Wait. So, no events here. Oh, Jesus. Okay. Sorry. Well, that was actually right. But I forgot to multiply times the probability of no events. So e to the minus m of t2 minus m of t1 plus h1. Okay. So, sorry about this, but everything sort of cancels out here when you look at this product, because e to the minus m t1 plus h1, well, somewhere you add it. You have the same thing with a different sign. And similarly for everything. So all these e to the minus mt terms disappear except for the very last one. So what we end up getting is e to the minus mt times product. Yeah. So this is what we get in the numerator. I'm sorry for being so confusing here, but does everyone understand this? No? Like why, sort of, what the logic is? Sort of take the different times and you just explicitly calculate the probability of having one event somewhere and then having zero event everywhere else. Okay. So then we put the two together. So this means probability so this would just be divided by what we agreed was e to the minus mt factorial. So we get these nice cancellations, and we end up getting n factorial times this product here. Okay. So now what we do is we divide both sides by h1 through hn. And we use the fact that mti plus hi minus mti is just this integral here. And then we let all the hi's go to 0. And we let all hi go down to 0. So what we end up getting is that, I mean, if we let all the hi go to 0 on the left-hand side, we just get the density. So we get f of S1, Sn, given nt is equal to n on the left-hand side. And now on the right-hand side, the only thing that depends on the h's is this difference, which we just noted is equal to this. So if we let hi to go to 0, this just becomes L of ti, or lambda of ti. Okay, we can just say limit as hi goes to 0 of m this is just equal to ti. And this is because of the property one of the properties of non-homogeneous Poisson process. So that's how we get that that the density is this term here. And that's how we prove what we want to prove. I don't know if it's useful to be going through this in such detail, because I highly doubt that you'll have to do something like this ever. But yeah, I mean, I just don't see it. But it is I mean, it's a good problem. And okay, so so let's do part B then, I guess. I mean, and of course, if this is the density, then the CDF will just be the integral from, so it will be m of ti. Right? Okay, so part B. So suppose that workmen incur accidents. So accidents are according to a non-homogeneous Poisson process with mean value function mt. Suppose further that each injured man is out of work for a random amount of time having distribution f. So out of work for time distributed as f. Let xt be the number of workers out of work at time t. And we want to find the expected value of x of t. Okay. So, first of all, let's nt denote the number of injuries at time t. And from part A, we proved that and so the time, the time of the injuries, of these n injuries, are distributed as n IID random variables having distribution f, let's call it g, I guess. G of x is equal to, they have this distribution. So, yeah. Okay. And now, yeah. Okay. Let's now consider any arrival out of these, any arrival out of n that occurs any injury that occurs at time s. Some time s where s is between 0 and t. So then, let's say P is the probability that injured person is out of work at time t. Okay, so then we need to condition on when his injury occurs. So we condition on, so we say probability out of work given injury occurs at time s times the probability that blah, 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 injury occurs at time s. Sorry, I'm going a little fast, but we're running out of time. So this probability is of course f of t minus s, right? Because he got injured at time s and he was still out of work, so or I guess it's F bar. So his injury, his recuperation time is more than T minus S. And that happens with probability F bar of T minus S. And then the probability that the injury has occurred at time S is due to part A just equal to lambda S over MT. This is just the density. This is what we calculated in part A. Okay. So this just applies for one person. So what would this be then? So, given NT. Given. Then this would just be however many people we have times this probability here, because these things occur independently. Because this is the probability that a person who arrives in time from 0 to t is out of work at time t. So if we have this many people arriving, then, well, you'll have the expected value will be, condition on that will be just the number of people times this probability p. Which means that the expected value of x of t is just the expected value of n of t times this probability p. Now, expected value of n of t is just equal to m of t. Times, and now we just wrote down what p is. So we can cancel these terms out, and this is what we're left with. So it's equal to this. Okay. Any questions? This is a hard problem, I know, and I'm sorry I did a terrible job at sort of explaining it. But okay. So I encourage you, if you have like questions about the homework, especially since I didn't have time to go through so much of it, to just come and see me whenever. I'm pretty free this week, and I'd be happy to sit down with you. And also remember to erase what I said about that first theorem, that they're independent Poisson processes. Just stick to what the book says, because I think I made a mistake. Okay, thank you.